Black holes are some of the most mysterious and captivating phenomena in the universe. These massive objects, often weighing between 2 to 4 times the mass of the Sun, remain invisible to us due to their immense gravitational pull. However, thanks to decades of research, we've gone from knowing almost nothing about them to being able to study them in greater detail. One of the most significant breakthroughs came when physicist Michio Kaku suggested that we might have finally glimpsed what lies inside a black hole. This discovery sheds light on what has long been a hidden realm in space. But before diving into Kaku's latest findings, let's take a step back and explore the history and the nature of black holes. Although many people have a general understanding of black holes, there are still significant gaps in our knowledge. The concept of a black hole was first predicted by Albert Einstein in 1916 with his theory of general relativity. However, it wasn't until the 1960s that the scientific community found concrete evidence of black holes. During this time, astronomers were studying the Cygnus constellation when they detected an unusually bright blue star emitting X-rays. Upon closer inspection, they realized that the X-rays were being pulled toward an unseen object, which turned out to be a black hole. This discovery provided definitive proof that black holes were real and not just a product of Einstein's imagination. This was a groundbreaking moment, as it revealed the existence of these colossal objects in space, which had remained largely theoretical until then. The black hole in question, named Cygnus X1, is located about 6,000 light-years from Earth and is more than 15 times brighter than the Sun. Its immense mass and density create a gravitational pull so strong that not even light can escape from it, giving it the name black hole. The nature of black holes is both fascinating and terrifying. They are regions of space where gravity is so intense that nothing, not even light, can escape. Any matter or radiation that ventures too close is pulled in, never to return. This concept has made black holes both an alluring and ominous topic for scientists and astronomers alike. The question then arises: are we in any danger? While the nearest known black hole to Earth is located between 500 to 1,000 light-years away, it is still close enough to raise concerns about the potential risks they pose. In 2021, scientists were able to capture the first clear image of a black hole, specifically the one in the M87 galaxy. This image, which was captured over several nights, provided significant insight into the structure of black holes. Researchers were able to combine multiple images to create a more comprehensive picture, revealing that black holes are not just massive voids, but rather complex structures with 3 distinct layers. The first layer is called the event horizon, the point beyond which nothing, not even light, can escape. Once something crosses this boundary, there's no turning back. The second layer is known as the photon sphere, where light can orbit the black hole due to its intense gravity. The third and final layer is the singularity, the core of the black hole, where matter is compressed to an infinitely small point, and the laws of physics as we understand them cease to function. What makes studying black holes even more challenging is that each one is unique. While they share the same basic structure, the way each black hole behaves can vary widely. This makes it difficult to study them directly. Scientists can only observe the effects of black holes on their surroundings, such as the radiation they emit and the behavior of nearby gas and dust. Sending a probe into a black hole is impossible because once anything crosses the event horizon, it is pulled into the singularity and destroyed. Despite these challenges, researchers have developed various theories about how black holes form. One of the most accepted theories is that black holes are created from the collapse of massive stars. When a star exhausts its nuclear fuel, it no longer has the energy to counteract the force of gravity, causing it to collapse inward. This process leads to the formation of a black hole, a dense object with a gravitational pull so powerful that it warps the very fabric of space and time. In summary, black holes remain one of the most enigmatic and compelling areas of study in astrophysics. While we've made great strides in understanding their existence and basic structure, many questions remain unanswered. With each new discovery, we get a little closer to unraveling the mysteries of these cosmic giants. Gravity continuously pulls inward, causing the star to collapse upon itself, becoming denser as it does. If the star is massive enough, this process can continue until it forms a singularity. To better understand the nature of black holes, NASA scientists focused on the center of the universe, specifically the M87 galaxy. Astronomers observed a massive whirlpool of extremely hot hydrogen gas spinning at a staggering speed of 1.2 million miles per hour. The intense force of this rotating gas disk should have caused it to fly apart in all directions, but it didn't. Scientists discovered that a massive object at the galaxy's center was holding everything together, preventing the gas from dispersing. This massive object weighed as much as 2 to 3 billion suns, and it could only be a black hole. However, black holes may not be as simple as we once thought. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to describe a rotating black hole. Kerr demonstrated that a spinning black hole wouldn't collapse into a point, as previously believed, but instead into a ring-like structure, known as the ergosphere. In this rotating disk of matter, diffusion forces would prevent further collapse. The ergosphere is the region surrounding a black hole where the laws of physics begin to break down. One of Kerr's most intriguing predictions was the existence of an Einstein-Rosen bridge, also called a wormhole. A wormhole is a theoretical shortcut through spacetime that could connect two distant regions of the universe, or even parallel universes. The idea suggests that if someone were to fall into a black hole, rather than being crushed into nothingness, they could be sucked through a tunnel within the ring of fire and emerge from a white hole in another universe. To understand this concept, we must first examine Einstein's theory of relativity. According to this theory, objects with mass warp the fabric of spacetime, creating gravitational fields that attract other objects. Imagine spacetime as a piece of paper with points placed on it. The path between the points represents how objects move through spacetime. But what if you could fold the paper in half and create a shortcut between these points? This basic idea describes a wormhole, an instantaneous connection between two distant places in spacetime. Wormholes aren't just a science fiction concept. They are actually a prediction of general relativity, though none have ever been observed. The issue is that wormholes are inherently unstable and would collapse quickly. However, the presence of an Einstein-Rosen bridge could suggest that black holes might not only be cosmic vacuums but could also serve as gateways to different regions of spacetime. So, could we one day use a wormhole to travel through the universe? Unfortunately, the answer is likely no, at least not yet. Even if we could stabilize a wormhole, it would be impossible to travel faster than the speed of light. Einstein's theory of special relativity sets the speed of light as the ultimate limit for how fast anything can travel through spacetime. However, the idea of wormholes and black holes as pathways to other parts of the universe, or even to different times, remains an exciting and debated topic among physicists. The idea that there could be shortcuts through spacetime, enabling travel across vast distances or even into the past, could revolutionize our understanding of the universe, if we could ever make it a reality. One particularly fascinating concept is the mongrel wormhole, named after Roy Kerr, who first described it using Einstein's equations of gravity. This type of wormhole is a speculative tunnel through spacetime that could connect two distant points, such as two different universes or even two separate times within the same universe. The mongrel wormhole is often depicted as a ring-shaped doorway, similar to the mirror in Alice in Wonderland, where walking through it could transport someone to a world with completely different laws of physics. Despite the excitement surrounding wormholes and their potential for interstellar or time travel, the idea is not without its challenges. Some physicists have pointed out that wormholes, especially traversable wormholes, might be unstable or difficult to navigate due to the extreme radiation and subatomic forces surrounding their entrances. Critics argue that Einstein's equations of gravity, used to describe wormholes and black holes, are limited to gravity alone and don't account for the quantum forces that govern radiation and subatomic particles. To fully understand these phenomena, a new theory is required, one that can combine the laws of gravity with quantum mechanics. This theory, known as a theory of everything, TOE, aims to unify Einstein's theory of gravity with quantum theory. One promising candidate for a TOE is string theory. String theory suggests that subatomic particles are actually tiny, vibrating strings, and the universe operates like an orchestra, with different particles corresponding to different vibrations of these strings. An intriguing aspect of string theory is that when a string moves through time, it distorts the fabric of space, which can result in the formation of black holes, wormholes, and other phenomena predicted by Einstein's equations. This means that string theory not only unifies gravity with quantum mechanics, but it also provides explanations for many of the mysterious phenomena we observe in the universe. However, string theory does introduce some complexity. It requires the existence of 10 dimensions of spacetime, far beyond the 4 we experience in our everyday lives, 3 spatial dimensions and 1 time dimension. Though it's difficult to imagine what these extra dimensions might look like, physicists have developed theoretical models that could help us understand them. One analogy often used is that of a 2-dimensional lake inhabited by fish, which are only aware of the lake's length and width. To the fish, there's no such thing as height, and they can't even conceive of a 3-dimensional world. Similarly, string theory proposes dimensions beyond our comprehension, potentially explaining some of the universe's most perplexing mysteries.